Maybe I will temporarily turn up the video, my video, because the internet here could be unstable. So shall we start now?
Yeah.
Okay. First of all, thank you very much for giving me a good opportunity to give a talk in this workshop. And I'm very sorry that I cannot attend physically, and I hope I can have a chance to meet you in your future. So today I will discuss about some quantitative aspects of the hyperbolicity problem from the point of view of value distribution theory or nirvana theory. So this is a sketch of my talk. So let us start by giving a quick reviews about higher dimensional value distribution theory. So suppose it's a complex projective varieties and the Cartier effective divisor on S. We take L to be the associated line bonder. And suppose we fix an Hamilton matrix on L, and that's omega L is a chain class of L. So we fix a global section of L corresponding to P normalized, so that's a norm is less or equal than 1. Suppose now you have anti-olophic curve image, such as the image of Fe not totally contained is in support of D. So value distribution theories MS studies frequency of intersection of the curve F and D. The starting point is the Poincare-Lelong formula. We have this in equation in the sense of current. So you want to study the intersection between the curve and this means that you need to study the pullback of D on the complex planes. So under the condition that the image of F is not contained this in supposed D, we have a divisor. The pullback of F by D, we have a divisor on the complex planes. And if you count total number of intersections, it could be infinite. So the point here is that you restrict to count the total degree only on the disk, and then we study the growth of that number when the disk has radius tend to infinity. So in this sense, first you sum the k truncated degree of divisor on this. So, and then you take the logarithmic average. They give you the counting function of the counting function of the divisor if. So the value distribution theory is then established by studying the relation between three associated functions. First one, we count is the truncated counting function. It gives you the frequency of intersection between F and D. The next one is the proximity function of F for the divisor D. It's given by that integral on the disk of quantities log 1 over norm of F. This mark above with F. And since we normalize the global section sigma, you always have proximity function here is positive. And lastly, we can define the order function of F with respect to the line under F as the logarithmic interest of the integral over the this delta t of the pullback of the transform omega F, and it turns out that the definition is verified up to, modulo up to about the term. So the truncated counting function gives you the frequency intersection between F and D. The proximity function measure actually how large this measure the point on the complexity view sent by f to the point very close to this, and the other function geometrically it gives you the logarithmic average of the area of the image of the this by the f measured by the Hamilton matrix that we fixed before. If you are, we normally, if you work in CPN and we work with LC audif, if you test homogeneous coordinates of CPN and suppose you have a reduced representation of the orthogonal curve F from C to CPN, if it's a divisor D of CPN by defined is by a homogeneous polynomial of degrees D, then you can translate the above definition of the three counting function, the truncated counting function, the proximity function, and for the order function, normally we play with Cartan order function. So this one it gives you it gives by for the Cartan order function is a compute with respect to the Fubini study matrix odds are 1. And if you play with OD, you should have D times the counting function. So the Nirvana theory consists of mainly two main theorems. The first one tell you that the other function of f with respect to the line boundary f is roughly equal to the sum of the counting function plus the proximity function, the loss in boundary term. And since the proximity function is positive, we have thus counting function of f with respect to this is bounded from above by the other function. And if you define the defense of D with respect to f by taking the limits of 1 over n over t, then the quantities is 0, 1. So another important corollary of the first main theorem is that if you have the bit line boundary of E on S, then the other function of f with respect to E, it dominates the other function of other line boundary on S. And in other direction, in the so-called second main theorem, we aim to find upper bound for the counting function in terms of the sum of certain counting function. So such question were established in several situations, but in zero is very open. So the classical result of Cartan tell you that if you have a family of Q hyperplanes in zero projection here means that you have intersection of families of n plus 1 in this family is empty. So if you have a linearly non-degenerate curve f, meaning as the image f is not contained in any hyperplanes, then you have a second main theorem estimate is the following. You have Q minus n minus 1 TFR bounded from above by the sum of the truncated n truncated counting function of f with respect to Hi, and this inequality is hold true outside Lorentz success of zero infinity of finite level measure. So TFR here is a Cartan order function. In the case where n is equal to 1, you can refer that's a Nirvana second main theorem. In this case, one-dimensional case for non-constant monomorphic function f and the families of at least 3 distinct points, you had the second main theorem optimus. And later, this result of Cartan is generalized into the nonlinear case. Namely, we place with hypersurface rather than hyperplanes. The first one was established by Eremenko Sodin by potential methods, and Drew is another result of Drew extended result using method from the Fontaine approximation. It's very important remark that in this kind of second main theorem estimates units many components in and the right hand side, the inequality. So you need at least n plus 2 components. So here in the table, you can see the corresponding between the quantitative aspect and the quantitative aspect of the hyperbolicity problem. For instance, in one-dimensional case, you have the little Picard theorem tell you that Mirovic function avoid 3 distance points is constant. And in quantitative aspect, you have the Nevalina Second Main Theorem estimates just mentioned above. And in CPN, you have the Boran theorem that tell you that if the Olympic curve avoids the families of n plus 2 hyperplane in zero projection in CPN, then its image should contains in one diagonal hyperplanes. And in quantitative aspect, we have second main theorem. So if you expect the logarithmic Green-Griffiths conjecture in CPN, then you should expect also a second main theorem for algebraically non-degenerate Olympic curve in the setting generalized hypersurface of degree at least n plus 2. And similarly for the Kobayashi conjecture, if you expect the logarithmic Kobayashi conjecture, then you also could expect a second theorem for non-constant Olympic curve and the generic hypersurface of degree greater than 2n minus 2n plus 1. So the later two later SMTs is still in our dream. The more optimistic version of second main theorem we could hope is a conjecture which contains a fundamental conjecture of anti-curve. So Griff, Win command Noguchi, with aspects just for projective probability S and for simple normal crossing divided D on S for algebraically non-degenerate anti-Olympic curve into S can have a second main theorem type estimates for the counting function for the other function of S with respect to the canonical line boundary KSD. And in the right hand side, this is a truncated K0 truncated counting function. So of course, the best truncation level we can expect here is 1, but this is question is perhaps too difficult at the moment. Even in Cartan's second main theorem, we can only get truncation level n. So as I said before, when D has at least a dim S plus 2 component, this estimate 2.1 was established in several situations. So it's a case where the abelian practice is case the canonical boundary is trivial, then the conjecture will confirm by Xiuzhang and then Winkelmann, Yamanori, Noguchi with optimal truncation level 1. So this is a more optimistic quantitative version of the logarithmic Green-Griffiths conjecture that we can expect. Not last, in the case where S is a projective space and there is hypersurface D of degree D, then the estimate 2.1 reads as D minus n minus 1 TFR is bounded from both by counting function of f with respect to D modulo bounded term. And here TF here is a categorical function. So this gives you the defect relation of f with respect the defect of f with respect to D is bounded from above by n plus 1 over D. So it means that the last degree and then the smaller the defect, the smaller the defect, it means that the curve meets these very often. And if you test the limits of 2.3, when the degree D tends to infinity, you get just the defect of f with respect to this when the degree tends to infinity, you get 0. So it means that the degree larger and larger, the defect smaller and smaller, and the curve meets the curve more often. So even the axis of this estimate 2.4 is very open. And I only know one result of Yamanoi in a two-dimensional case. So he gets thus for generic curve D of degree D large enough in CP2, D here could be mass effective more than 100. For instance, then for algebraically non-degenerate race holomorphic curve F from C to CP2, we have this effect relation. But the important thing is that in the denominator you have square roots, 4 square roots of D, so that if you take D tend to infinity, then this tend to 0. But still, this estimate is not as good as 2.3. We know if you need something divided by D. So let me now talk about some recall some facts about Z differential and how to use it to deal with this question. So in a projective variety S complex one, we have if you have a simple normal divisor on S, let's consider the logarithmic Green-Griffiths KZ bundle along diff. I think Cochran we talk about this one many often. So let me some very quick on this part. So a global section of this bundle is contains a logarithmic KZ bundle. So this one has order k and a weighted degree m. So locally you can write out is weighted homogeneous polynomial of variable dz log zi, dk log zi, and dk log zi, dk zi, sorry. And if you assign k, the weighted degree of dk log zi and dk zi, then this forms essentially weighted homogeneous polynomial. So it's this empty we are found in the compact case. And this classical as okay, global section of this bundle will provide you algebraic differential equation with any entropy curve f from C to S avoid D must satisfy. But furthermore, we also have a quantitative result for this statement. So if you have a zero smooth hypersurface of the degree D in CPN and entire function f from C to CPN, this kind of result can be generalized to scale of projective variety without difficulty. Suppose that you have a global logarithmic jet integer with weighted degree m and the vanishing order to the ampolar bundle CO1 m theta. Then such as P up with n jet of f is not identical to 0. Then we have the second main theorem estimates of the bond TFR less or equal than m divided by n counting function of f with respect to D with truncation level 1. Modulus bounded term, another term. It's important to remark here that if you have higher vanishing order, then you get better second main theorem estimates. So then it's very natural to add what kind of the best ratio m over m theta we can have here. So certainly from this one, you can deduce the fundamental vanishing theorem. If you have a global section of a Green-Griffiths KZ bundle vanishing and some ample line bundle, yes, we don't care about in quantitative version, we don't care about the vanishing order. If you have some negative vanishing, then you have algebraic differential equation. And in the case where this empty, you are in the compact case. So from the a quantitative version of the fundamental vanishing theorem. Lastly, you can the technique on hyperbolicity problem, Green-Griffiths conjecture can give you not only qualitative but also quantitative result. So if you have a good jet differential form, from that you can deduce second main theorem. So to have a good jet, you have the condition that the degrees is very large compared with the dimension. Under this condition, you have second main theorem. The first result is the direction is established in the case where F is algebraically non-desired race, and later for that then you can deal with the case where the anti-curve is non-constant. So namely, they establish a quantitative result for the logarithmic Kobayashi conjecture. But the degree is very large, such as this kind of estimates is really very, very far from the one you expect, like in the fundamental conjecture for anti-curve. Remember, as we expect something like d minus n minus 1 TFR bounded from above by the counting function. Here, if you have degrees very large, then the quantity d minus n minus 1 is very large. And in the no result, we only have the 1 on the left-hand side for the counting for the other function. So to guess the fundamental conjecture for anti-curve, Green-Griffiths jet with very high vanishing order is around d minus n minus 1 equated degree. And at the moment, it's really difficult to guess that. The reason is that in strategy to deal with the logarithmic Green-Griffiths or Kobayashi conjecture, we start with some jet with very high vanishing order. But after that, for example, if you apply some slanted vector field with low power order, we need to apply enough time to produce really good sets. So in this sense, you may have not good vanishing order at the end. So we need to apply essentially n time vector field to get the one good set. So at the moment, we don't know if under the condition at non-degenerate, degenerate, whether we can have the jet with the vanishing order like phi dm, where phi d tend to infinity at d tend to infinity. If we can get this, then we can at least get the unsynthetic version of the fundamental conjecture for anti-curve, the defect relation version. But still, this is may require lots of work. So producing a good jet with a very high vanishing order, perhaps difficult. We move to another question where we really don't need so high vanishing orders. That is the application of jet differential form in studying the distribution of geometry of minimal surface. So let me recall some facts about minimal surface and scale math. Suppose now you have S a regular surface in R3. So the classical Gauss map of S is the map from S to the unit sphere, sending S by S to the unit normal vector of S as P. Sorry for the not so beautiful picture. So the surface S is minimal. We have a lot of criteria for the minimal. By definition, first, this is minimal. It is a minimal area for on small perturbation. So we have other condition like it should satisfy the Lagrange equation, etc. But we want to apply the theory to study the Gauss math. So Now we let ds is a matrix on as induced from the Euclidean matrix, and you let use and v UV the local system of isothermal coordinates on S. Isothermal is means that you can write out ds square as a lambda square of du square plus dv square. Here lambda is some positive smooth function. If you for isothermal coordinates, you can use holographic structure and to mesh S become open Riemann surface. This is a classical result of Sin's function. And now if you use the stereographic projection from the sphere to CP1, and you can compose this projection with the map, and to get the map from the Riemann surface S to CP1. And this is classical results as S is minimal and if and only if, and this map C is meromorph. So therefore, we have many analogs between scale mass and studies the result of scale mass and meromorphic mapping. For example, we can aspect some analog of Little-Picard theorem. The question you should ask is in Little-Picard theorems, the map non-constant meromorphic map can avoid only 2 points. So the question, the scale mass of S can avoid how many points? The first result in this direction is the result of Osman's. I tell you that okay, the complements of the scale maps of the non-flush minimal complex minimal surface in R3 is of logarithmic capacity 0 in CP1, and thus this is enough to deduce from this one the classical Bernstein theorem. We tell you the graph of the real function on the whole plane 2, which is also minimal surface in R3 must be plane. So the result of Osman is improved later by Xavier. When he proves that okay, the map G can omit at most 6 points, and finally Fujimoto he does the optimal result that G cannot miss at most 4 points, which was another conjecture, and this result is solved by looking at the example of such surface. So now we are passing to the higher dimension. When you have the surface M, immersed is the Rm. So let's be oriented to real two-dimensional differential manifolds immersed in Rm. So first, we have the one corresponding between the sets of oriented two planes in Rm passing through the origin, and quadratic on the m-1 dimensional projective space. So you can now we identify oriented two planes in Rm passing through the origin with a point on the quadratic. By this method, for a point P in the surface M, after parallel translation mapping P to the origin, we can identify tangent planes of M as a point P with an element of the quadratic. And that gives rise to the definition of the generalized scale map of the oriented of the surface immersed in Rm. And similarly to the one-dimensional case, this the surface is minimal if and only if the generalized scale mass is holomorph. So that's why now we can employ no sadness in hyperbolicity problem to deal with the question of the distribution of the scale math. And so the first result, very classical results, is due to Fujimoto and Drew. So they prove that a GeoMath, a non-flat complex minimal surface in Rm can omit at most m times m plus 1/2 hyperplanes in general projection, and this number itself. So first, Fujimoto proves this result for the case where f is limitless non-linear race, and Drew prove this statement in general case. So in this view, it's very natural to ask a question about whether we can replace families of hyperplanes by only one hypersurface, zeroth hypersurface. So we can conjecture that for a complex minimal surface in Rm, and it's a GeoMath, suppose that this GeoMath avoids the zeroth hypersurface of large enough degree, say d greater than m times m plus 1/2, then g here should be constant. And we can think about this one as an analog of the logarithmic Kobayashi conjecture for GeoMath. So using that differential, we can prove this statement under condition just the degree d is large, very large compared with the dimension. So the degree bar we get here is essentially the same as the degree bar above for the logarithmic Kobayashi conjecture due to prove back and then. So let me talk a bit about the ideas of proof and how can we improve this degree bar for the question. First of all, it's enough to work in the case where m is a unit list. The reason is that if you look at to the universal coverage, universal cover of m, we have only three situations. Either is unit list, the C or CP1. But we don't have compact minimal surface in Rm, so we are in either the unit list or C. For C, we is a setting of anti-holographic curve. So this is also the hyperbolicity question. And now we play with the unit list. Because the key estimate is that if you have jet logarithmic jet of the vanishing order m theta, then you have estimates for the norm of as for the modulus of p g and f power 2 over m theta times with the norm at power 2. The important point is that we have the power 2m over m theta here. So above we have 2 times the weighted degree, and in the denominator we have the vanishing order. And it turns out that we only need condition that the vanishing order is greater than 2m to get that the integral over the unit list of these quantities is finite. And if you employ a classical result of estimate of Yelf, then give you really a contradiction. So in the question of GeoMath, what we need to have is a global section of Green-Griffiths bundle with the vanishing order m theta greater than 2m. So we expect this weaker vanishing order compared with the previous version when we need to find vanishing order is d minus 1 minus n minus 1 m. So in recently we have a lot of improvement in the degree bound concerning Green-Griffiths and Kobayashi conjecture. So certainly it should provide also a result on the degree above of concerning the Gauss map. So finally, let me if you enter to your PhD work, then it turns out that we don't need anymore the vanishing order on ample vanishing on ample bundle. So suppose now we are working with F algebraically closed field that is zero being complex with respect to a non-Hermitian valuation. Is the projective variety defined over F and the simple normal cross divisor on this. Just an analog of anti-curve. Here we have the analytic curve F, and we want to study the variety of analytic map from F to its avoid leaf. We have a lot of analogs between analytic map and anti-map. For instance, an analytic map from F to P1 avoiding 2 points, then it must be constant. So remember for little Picard theorems in complex setting, it need the middle fit map must avoid 3 points. But here we have better. We only need to require us F avoid 2 points. And if F avoids n+1 hypersurface in general projection, then it must be constant. So this statement is much stronger than the one we have in the complex setting. So the analog of the Kobayashi conjecture in this non-Arminian work is just for generalist F, these degrees at least 2n if F analytic map avoid into a CP, F PN avoid leaf, then it must be constant. In this setting, we still build logarithmic Green-Griffiths K-jet bundle. But the important thing is just for the vanishing theorem, we don't need any negativity with this just for the vanishing theorem. So namely, if you have logarithmic jet differential form of order case and weighted degree m along this, namely you have a level section for the Green-Griffiths K-jet bundle, then immediately you get algebraic differential equation for analytic map avoid leaf. So in this sense, I think you can apply also the techniques, recent technique on the study of hyperbolicity problem to the question, and since we don't need any negativity with this test, we can expect a better result. So that's the end of my talk. Thank you very much for your attention.
Are there any questions? I had a question. Do you have any intuition for why in the non-Archimedean case you don't need the negative twist for the vanishing theorem? Like
Yes.
It's surprising. Yeah,
yes, because in the non-Archimedean works, the definition of the positive function and the order function is much easier, very much simple than the complex setting. We don't need to have we don't need to take in the logarithmic average, so that we have the so-called logarithmic derivative lemma in very simple form. So that you really don't need any with this just.
Thank you. If there are no more questions, let's thank our speaker again.